Good morning, everyone, and welcome to our EU Green Week 2026 partner event entitled Digital Innovations for Soil Health. My name is Zafiro Vaxevanidou from ENA Development Consultants, and I'm the Communication Manager for WHEATWATCHER and NitroScope projects, and I will be moderating today's webinar. Thank you for joining us from across Europe and beyond to discuss how digital technologies can contribute to healthier soils and more sustainable agricultural systems. This event is organized in the framework of EU Green Week 2026, whose theme is this year is investing in nature. Healthy soils are one of our most valuable natural assets. They support food production, biodiversity, climate resilience, and rural prosperity. Today's webinar will showcase how European research and innovation projects are developing practical digital solutions that can help farmers, researchers, and policymakers to better understand and manage soil resources. Before we begin, a few housekeeping notes. This webinar is being recorded and may be shared through the participating projects' communication channels. Participants are welcome to submit questions throughout the event using the Q&A function. We will address as many questions as possible during the discussion session at the end. All personal data related to registration and participation are handled in accordance with GDPR requirements. We have an excellent program ahead of us, featuring 4 Horizon Europe projects, 4 Mission Soil projects that are working on soil health, digital agriculture, and sustainable farming innovation. Let us begin. Our first speaker is Dr. Antonios Morelos from Ghent University. Antonios Morelos holds a PhD in agricultural engineering from Aristotle University of Thessaloniki and is currently a postdoctoral researcher in the Precision Soil and Crop Engineering Group at Ghent University, working closely with Professor Abdul Moazen, who is the coordinator of both WHEATWATCHER and NitroScope projects, and Adonis is the scientific coordinator of WHEATWATCHER project. His expertise covers smart agriculture, artificial intelligence, IoT sensors, proximal sensing, remote sensing, and soil and crop monitoring technologies. His work focuses on transforming scientific advances into practical solutions that support sustainable and data-driven systems. Today, he will present potential of proximal soil sensing for fertility zone delineation in wheat fields. Andoni, the floor is yours.
Good morning. Thank you, Zafiro. Thank you for the introduction. Let me share my screen if I may. I want to...
Yes, it's perfect. It's full screen.
Perfect. Thank you very much. I really don't think I need to introduce myself again. I had to say I'm Antonios Morelos. As Zafiro said, a postdoctoral researcher in the group of Professor Moazen in Ghent University. Today, I'm going to present to you the potential of proximal soil sensing for fertility zone delineation in wheat fields, which is part of the WHEATWATCHER project. Okay. Let's start first with WHEATWATCHER in a nutshell. WHEATWATCHER is a Horizon Europe project under the Soil Mission platform, developing an integrated digital monitoring system for wheat production, linking soil health, plant health, and food traceability from field growth to floor production. The goal of WHEATWATCHER is to monitor soil nutrient status, chemical and biological stressors, and their effects on the wheat crop performance and grain safety, providing practical decision support tools for farmers, mill owners, and policymakers. The core concept is soil sensing. After soil sensing, plant monitoring, plant sensing. Then we have data streams from two of those, and we create data fusion models and machine learning models. We develop our maps and actionable decisions for a safer wheat value chain. So this is the approach. Very quickly, I will say that we basically have three platforms: a remote sensing, a proximal mobile sensing, and a proximal stationary sensing platform. The mobile sensing platform has two branches, basically, the soil robotic platform and the plant robotic platform. Today, I'm going to talk to you mostly about the soil robotic platform, but all of them create data streams which feed our chemometric models, our crop growth models, and our artificial intelligence model in order, as I said, to create actionable decisions for farmers, for wheat production, to enhance the wheat production. So we have our project is spread in 4 countries. We have 4 pilot sites, so 4 use cases as well. We have employed 5 fields of different soil properties in Belgium, in Flanders, for the monitoring of the soil nutrients. So basically, this is the baseline. We have employed 2 fields close to Nestos River Delta in Xanthi, Greece, where we monitor the salinity stress. We have 2 fields in areas with non-contamination in Silesia, Poland, for the monitoring of the heavy metals and the total petroleum hydrocarbons. And finally, our last pilot site is 3 fields with non-over-application of fertilizer in Demmin in Germany, where we are monitoring again the nutrients, but as a stressor from the over-application. So now digging into the proximal soil sensing technologies, we have 2 proximal soil sensing platforms that are being deployed in the WHEATWATCHER. The mobile proximal sensing platform, which consists of the online mobile multi-sensing platform and the soil crop sensing robot. This is what I'm going to talk to you about today. And the stationary proximal sensing platform, which is already even developed within WHEATWATCHER, and it's a multi-sensor stations for continuous monitoring of nutrients and soil physical properties. So we basically cover spatially and temporally the field. So going on the online multi-sensor soil sensing platform, we are using the platform that was developed and patented by Professor Abdul Mazen back in 2006. And it is equipped with a gamma ray detector, an RTK GPS, a visible near-infrared spectrophotometer, and a depth sensor at load cell for the estimation of bulk and bulk density. It measures properties in a defined depth, which we chose to be 10 centimeters, pretty much like surface soil, and with a temporal resolution of 1 Hertz. So we have basically 1 reading per second. So we have very high resolution sampling. And we use this for the prediction of the following properties of the moisture content, organic carbon, pH, calcium, magnesium, potassium, phosphorus, sodium, the soil texture, and as I said before, bulk and packing density. So what are we doing? What is the pipeline from online spectra to soil property prediction? First, we scan the soil in the fields. Then we take some samples, soil samples from the online scanning, and we send them for lab analysis, so we have the soil properties. After that, we go, or in parallel, we are doing some spectral cleaning and pre-processing. So maybe some misalignment, we are using the sensor online. So we have probably sometimes some misalignment between the 2 sensors, the visible and the near-infrared sensor. We have algorithms to cover for that. Or even sometimes for the moisture content and everything. And the preprocessing is for the noise that is captured by the sensors using some filters like statistical A, SNV, second derivative, so on and so forth. And after that, we are applying data augmentation, where we use spectra from our own custom soil spectral library, the one that we have built over the years as a group, based on mostly on the Mahalanobis distance between the samples that we have collected and the samples that we have already in our stock. And then we are creating the models using either machine learning techniques or PLSR. And from there, we can go to the prediction of the soil properties using the online spectra and finally to the mapping. So here we have some results from this from last year's scanning of the Belgian field in Flanders. On the top row, you can see the low resolution, let's say, maps. You can see they are quite smooth. They can show the variability, the in-field variability of the properties. And in the bottom row, we have the respective prediction maps as were captured by our models, by our PLSR model. I will not go through details in that because I will need the time to show also the rest of the equipment that we are using for the proximal soil sensing. So in a nutshell, what you can see is that we have a very high resolution maps. We capture in very high detail the variability, the within the field variability. So the predicted for here you can see the moisture content, the organic carbon, the phosphorus, pH, and calcium. And so the maps reveals the spatial patterns in soil condition and fertility related properties that can support site-specific management. And based on these fertility maps, we decide where we will install the stationary platforms of WHEATWATCHER, where also we will monitor the fields temporarily. I will now talk about the online nitrate sensor, which is the second innovation of this project. This is the machine that you can see on the left side. And you can see that it has two compartments. You can see like the two black caps. And you can see that there is also a selector that guides pretty much the soil in one of the two caps. And basically what it does is taking through the soil sampler that you can see on the right side, which is a hydraulically monitored, like a motioned soil sampler. Soil falls into the sensor. It mixes with water. The soil solution is pumped in a cavity or in a sensor cavity, and then we get the reading from an electrochemical sensor. Here you can see the architecture a little bit more graphically and easier. So as I told you, there are two compartments. Let's say that the soil falls, the selector is heading towards the left compartment. It falls into the first black cap, the soil, and then water is added by a water tank and it's mixed. And then we create a homogeneous mixture of 5:1 ratio, 5 water to 1 soil. And then this solution, the soil solution, is guided through a filter to the measuring cup where we get the readout to the measuring cavity, from the measuring cavity of the nitrate. And then the selector goes to the other side, and exactly the same cycle happens to the other side. And while the process is happening to the right side, on the left side, we have also a cleaning cycle for all of the compartments. Here you can see how this machine is now operational in the field. I forgot to tell you that this machine is basically an extension to the already existing multi-sensor platform that I have showed you before. So yeah, let's see the video. So you can see in the front, the red and the green is the multi-sensor platform with a subsoiler. And here you can see the soil sampler and the nitrate sensor. You can see how the sample is being collected from the soil. You can see that in front we have employing the multiple plower in order to smooth a little bit and create better trenches for the soil to be captured by the soil sampler. And eventually up, directed inside the nitrate sensor. And I think now we can even have some sound. Because you will hear some mixing. This is the mixing of the soil with the water. And at the same time, you can see that the selector is going to the other compartment for the next measurement. And then the processes going on. So for that, we have an online monitor to monitor all of the processes and all of the sensors of the multi-sensor platform that I showed you before with a newly installed online nitrate sensor. And before going to the field, of course, we have to create a calibration curve where we take the electrochemical sensor. We have two of them. I can even show you the electrochemical sensor. It's these pen-looking thingies here. These are the sensors. So basically, the water is going through this filter inside this cavity, and then we get the readout from the electrochemical sensor. And so first, before going in the field, we calibrate the sensors in the laboratory in order to have like a calibration curve to correlate voltage to concentration, to nitrate concentration. Finally, we have the soil crop field sensing robot, which is an autonomous robot, inter-row sampling robot, and is developed on ROS2 for navigation and localization. It is GPS-based, that it is, has path planning and basic obstacle avoidance. And for soil, it employs a visible near-infrared penetrometer and a gamma-ray sensor. The visible, you can see the penetrometer is right here. It goes like from the, I don't know if I have the pointer options. Yes. So like here, you can see the penetrometer, and this is a close-up. How it looks like. It has a sapphire window through where we have like the fiber optics, and we capture in the soil spectra while it penetrates into the ground, and also the resistance. Additionally, we have a gamma ray detector that it is continuously measuring the horizontally, like it takes the gamma ray emittance from the soil in 0 to 30 centimeters. And finally, now it is under development. We're trying to install, our colleague is trying to install a stereo camera and a hyperspectral camera for crop 3D reconstruction and also for crop hyperspectral scanning and monitoring of the diseases. Here it is how it works. So here you can see, no, maybe you can see how it navigates through the sampling point. And here, if you try, you can see in the middle where I showed you before the penetrometer, you can see the penetrometer penetrating the ground. It is kind of difficult. And in the same time, you can see how with the depth, we get the force and also the spectra. Here you can probably see the penetrometer going inside, penetrating the ground. So the take-home messages is that online proximal soil sensing allows us to capture spatial differences in nutrient availability and soil conditions before we seed it. These differences can be translated into fertility zones and can be used to guide the placement of stationary sensors and targeted monitoring points. And during the growth season, wheat growth and behavior can be monitored across these zones to understand crop responses under different nutrient, moisture, and contamination or stress-related stressors. So WHEATWATCHER basically links, this is the takeaway message, links pre-season soil variability with in-season crop performance and stress response. Thank you so very much for your attention. Zafiro, back to you.
Thank you, Adoni. Thank you very much for this insightful presentation and for demonstrating how proximal soil sensing can support more precise and sustainable wheat production. Our next presentation comes from the STELLA project. It is my pleasure to introduce Christina Marcou from the Agricultural University of Athens. Christina is the leader of Work Package 3 of the STELLA project and has specialized expertise in precision agriculture and agricultural machinery. Through her research and involvement in several Horizon Europe initiatives, she has gained extensive experience experience in remote sensing technologies, UAV applications, vegetation indices, and environmental monitoring systems that support both farmers and environmental sustainability. Today, she will present STELLA Sustainable and Data-Driven Agriculture. Christina, thank you for joining us. The floor is yours.
Thank you very much for having me. Also, just to let you know, my voice is not at its best, so let me know if something that I say isn't heard enough or
Don't worry.
Any repetitions are needed. So let me share my screen. So right now you should be able to see.
Yes, but not full screen yet.
Yes, I'm trying. Great. Do you see it full screen?
No, now it's presenter screen.
Oh. Wait. Yes, because it is shown in my other screen. Give me a second.
I think the display settings. Don't worry, we're here.
Let's try it again. I found the display settings.
Yes.
Now?
Swap. Yes.
Great. So this will be a presentation about the STELLA project. Some high-level information. STELLA at a glance. Mainly is a Horizon Europe project developing real-time pest surveillance system that connects early warning, pest detection and response, all within one single platform. Some numbers, mostly boring. The duration of the project is 4 years from 2024 to 27 across 14 different partners in 6 use case pilots from 5 countries. And it's about 8 regulated and quarantine pests. The core system of the STELLA PSS is the early warning, that is main focus is on forecasting pest and disease risk using models, weather and IoT data. Then the pest detection system, which is detecting symptoms and pest presence through imagery, traps, sensing and app observations. And finally, the pest response system, where it provides risk-informed recommendations to support surveillance and phytosanitary action. So we're pretty stoked about the extensive about the extent of our partnerships since we are testing our technologies across Europe in many different countries and fields. Here you can see an overview of all our use case pilots. We will start from Greece, where we are focusing on olive trees with pathogens like verticillium and pseudomonas, and also the devastating disease of plane trees, about the Keratocystis platani, which is a quarantine pest. Then moving on to Italy, we have processing tomato as a crop and pathogen, of course, Ralstonia solanacerum, again a quarantine pest, which is really severe. These are the quarantine pests, these two. We move to regulated non-quarantine pests in France with grapes in vineyards, with the grapevine leaf roll disease and Candidatus phytoplasma. In Lithuania, in potato, we have the potato leaf roll virus. And in New Zealand, we have apples with Neofabra alba fungal disease. So STELLA actually what I just said, provides real-world test beds to evaluate the pest surveillance system and subsystems across different crops, regulated pests, and surveillance settings. So, the main question is what kind of technologies are being fed into the STELLA models and in the end help to make all the different subsystems. So, for example, we see that all of our use case pilots have installed weather stations and in a variety of sensors. Of course, we sense precipitation, wind speed, soil moisture contents. Then we have satellite imagery, mostly data from Sentinel-2 for all the pilots. Drone imagery is available in most of the pilots. The Eden Viewer is a very nice machine that is proven very helpful, making the AI models that I will show you in a bit. Then, of course, Pessel's smart traps and the crowdsourcing app as well. Now, all this data are being fed through different groups developing the models, and then we have the predictive models that are used in the early warning and daily risk indices, the detection models, which are image and sensor based, and the outputs is mainly in risk maps, alerts, detection layers, and decision support information. So the key point here is that STELLA connects different monitoring technologies into one workflow, simple, straight line. So data from sensors, imagery, traps, and field observations can support early warning, detection, and response in modern agriculture and forestry contexts. So this is the most interesting slide from our side, at least. Here I have the opportunity to show you how the STELLA PSS outputs are being shown to the user throughout the different subsystems. I will firstly draw your attention to the upper part of the presentation, starting as previously mentioned from data collection with IoT sensors, satellites, UAV, smart traps, citizen science. Mostly the IoT sensors and the weather station data are feeding the early warning models that can be seen in the far left corner here in the window. I will go into more detail about that in a bit. Its main output is a daily risk index. Then we go to the pest detection, which corresponds to the other two images exactly below the middle one and the far right one, where it mostly generates detection maps, inversion of heat maps, and in the case of the Eden Viewer, trajectory maps with the confirmed infestation or hotspots in, of course, field level. Then we have the pest response, which is category based. If it is a quarantine pest or a regulated non-quarantine pest, and it generates risk-informed recommendations and guidance. And of course, then the stakeholders like authorities, growers, advisors, researchers, and industry can benefit of the outputs of these models as well. So what we like to focus on is that the STELLA PSS is not a closed system. It is mainly being developed so that it can host external AI models, and not only AI models, of course, mathematical models as well. It supports data sharing and, of course, exposes standardized geospatial outputs. So let's go and see in detail what the outputs of each subsystem are. So the early warning system that you can see in the far left corner, mainly we will go from the far left window where we can see some high-level information about the pest, the crop, the coordinates of the field and the size. Right below it, we can see the percentage of risk being shown throughout the period that the user has chosen. So high, medium, low. Then we have in the colorful graph the risk level and its cumulated value. Again, for the risk level is from 0 to 1, 0 being the lowest and high being the 1 value. Of course, this risk level index, this daily risk level index is being calculated from the weather data and the models developed by UCSC. And in the graph right below it, we can see the weather trends that are being lively streamed from the weather station platform. And we have precipitation, humidity, temperature, leaf wetness, and one more very important aspect is that the user can see the distance from the closer weather station that these data are being taken from. Moving on to the pest detection subsystem, we have the satellite-based detection, where its outputs or the outputs of the models are mainly heat maps, informing the user about the presence and actually the intensity of the disease present on the field. Here in green, we see that there is a none to low presence of pathogen, medium with yellow, and high with orange-red. Of course, again, we have a detection history that the user can select and see the image of his field from previous detection, from previous days. And then if they press the Take Me to Action button, they will generate a very useful guide on what they can do to not worsen the situation in his field, and in quite some time to minimize its effects. Moving on to the hidden viewer-based detection, here the outputs are quite different from the satellite-based detection. We have a trajectory where you may be able to see from the lines drawn across the field. This is a trajectory that the hidden viewer mounted on the tractor has made, and all the different red spots correlate to actual detections of the models that the AI models that these data are fed through. Of course, again, we have a detection history and some high pilot details regarding the name of the pilot, the crop that's being cultivated, the pathogen, coordinates of the field, and the size of the field as well. So let's see now how STELLA PSS can support data-driven agriculture. Mainly, the STELLA strives to become an EU-wide digital collaboration entry point for testing digital tools that support plant pest and disease surveillance through early warning, detection, and response mechanisms. And where STELLA PSS now is valuable and relevant to today's event is that mainly targets surveillance planning through the use of risk indexes and forecasting outputs to help focus where and when to look. Further, making it possible that we can apply sustainable agriculture with less field interventions, less manpower needed within the field, and of course this translates to an increase in profit, long term of course. Secondly, it combines evidence sources, bringing together IoT, weather station, census data, satellite or UAV imagery, smart traps, and validated field observations, which are then fed through the early warning and detection models, which in turn offer a concrete pipeline backed by science. Thirdly, we have the support through the response decisions, where brought outputs according to pest regulatory status and stakeholder needs. Of course, the outputs are differentiated if the detection is about a quarantine pest or a regulated non-quarantine pest. And this strictly correlates to official plant health organizations like regional phytosanitary authorities, the ESA, the EFSA, BPO, national and regional networks. This support response decision helps the official plant health to stay connected with farmers. And finally, the STELLA PSS validates tools in real settings. This is very important for us because we use use case pilots and stakeholder feedback to assess model performance, usability, and uptake. Directly being correlated to field users like advisors and phytosanitary authorities, who rate the farmer towards minimal application of pesticides through established pest response protocols. So this was STELLA in a glance and what it can do to support data-driven agriculture. I hope that I didn't take too much of your time and I didn't bore you a bit with all the details. Thank you very much, and I am available, of course, for any questions in the upcoming time.
Thank you, Christina. Thank you very much for presenting the innovative work being developed within STELLA project and for highlighting the role of data-driven approaches in sustainable agriculture. Our third presentation will bring an important stakeholder perspective to soil health innovation. I am pleased to welcome Dr. Rita Barros Silva from APEMETA, the Portuguese Association of Environmental Technology Companies. Rita has been working in stakeholder engagement, environmental innovation, technology transfer, and European project implementation for nearly a decade. She has contributed to several initiatives promoting sustainable agriculture and environmental technologies, and currently leads Work Package 1 within the E-SPFdigit project. She holds a PhD in environmental engineering with a specialization in waste management. Today, she will present E-SPF digital innovations for soil health, what stakeholders tell us. Rita, thank you very much for being with us today. Please go ahead.
Thank you. Good morning, everyone from Portugal on the other side now. Thank you for joining us today. Let me start by introducing our project. E-SPFdigit is an Horizon Europe Innovation Action under the mission Soil. The project aims to develop and validate on-site digital tools for monitoring soil intended for food production, plants, and food-related contaminants. The project is not only about soil health as an environmental concept, it looks at soil health through the soil-plant-food connection. where monitoring can support sustainable farming, contamination prevention, and food safety. One important aspect of ESPFdigit is that it does not focus on a single parameter. It brings together agronomic parameters such as nutrients and contamination-related parameters such as PFAS, pesticide residues, and heavy metals. It also includes plant health and biological stressors. And this multi-stressor approach is particularly relevant when soil health is considered within the context of food production and food safety. ESPFdigit brings together several technology layers to support on-site monitoring and decision-making. One first layer includes on-site sensors for PFAS, pesticide residues, heavy metals, micronutrients, and soil water parameters. These sensors may be used as standalone sensors, but in the project, they are also integrated with field monitoring components. We have a robotized platform, multisensory platform designed to support plug-and-play soil sample extraction and analysis, bringing the sensor closer to field operational conditions. We have a ground robot and a UAV that add complementary monitoring capacities. The ground robot supports plant health monitoring, focusing on fungal diseases and abiotic stressors. The UAV supports mapping soil texture, crop stress, soil moisture, irrigation needs. And above all these field components, AI, machine learning, edge processing, earth observation, and microbiome-related data are integrated, modeled, supporting the interpretation of field and sensor outputs, and helps transform these multiple data streams into meaningful information. The final objective is not only to collect data, but to turn monitoring outputs into useful information for soil management decisions through a decision support system. Of course, looking at all these technological layers bring us to a question: under which conditions can these tools actually be adopted and used? And digital soil monitoring is not only a technical challenge, it also depends on what stakeholders want, value, and need and perceive. And this is why this work package 1 was designed to support one of this ESPFdigit project's first objectives, which was to conduct a systemic analysis grounded in stakeholder evidence. Through 2 European online surveys, interviews with the Industry Advisory Board of the project, and the feasibility and benchmarking analysis, we try to look not only at how stakeholders perceive soil health and contamination, but also at what they would need in order to trust, adopt, and use these on-site digital monitoring tools. I want to take also this opportunity to publicly acknowledge all these stakeholders that privately or anonymously participated in these surveys. Your opinion matters is really important to us in the sense that we have a realistic perception of current field reality. So the main basis of our work were 2 online surveys promoted roughly during the first semester of 2025, where we had a total of 851 responses across Europe. The first survey focused on soil practitioner and explored the needs, perceptions, and requirements related to on-site digital technologies for monitoring soil and plants. And the second survey took a broader farm-to-fork perspective, focusing on soil contamination, soil management practices, and strategies to reduce contamination. In parallel, the project mobilized an industry advisory board to bring external perspectives into the analysis. And this has supported the conduction of semi-structured interviews during the summer 2025 and helped complement the survey results with a more qualitative feedback from the different stakeholder groups. The evidence was also combined with a feasibility and benchmarking analysis. So the aim was not only to collect opinions, but to translate the stakeholders' perspectives into requirements for technology development, demonstration, and also communication. And the first message from Survey 1 was that relevance is not the problem. So around 80% of the respondents recognized the benefits of soil health, so the topic clearly matters to the stakeholders. But this awareness does not yet translate into operational adoption. Because, for instance, acknowledgement or awareness of the EU initiatives like the soil mission or the soil monitoring law is more limited, and the regular use of monitoring solutions remains very low. This gap is even clear for on-site digital sensors. Only a small share of the respondents had tested or used them periodically. And for E-SPFdigit, this means that the project is entering an emerging adoption space. So the challenge is not only to develop digital tools, but to help move from general awareness to practical capacity, trust, and use. The second message is that the strongest monitoring gaps appear precisely where the SPFdigit is trying to innovate. Stakeholders are more familiar with monitoring nutrients and crop development, but experience is much lower for PFAS and also more limited for heavy metals and pesticide residues. At the same time, laboratory analysis remains the most established monitoring approach, while the on-site digital sensors, the proximal solutions are still much less familiar and rarely implemented. So our project is working on the intersection of these two gaps. We have contaminants that many stakeholders have limited experience monitoring, and digital tools that are not yet part of the routine practice. And this means that the project needs to demonstrate not only technical performance, but also to help build awareness, interpretation capacity, and confidence on these on-site monitoring procedures. The third message from Survey 1 is that common barriers do not necessarily mean identical adoption priorities. Cost, training, access to equipment, cooperation, public funding, these were all important barriers, but when we look behind the averages, different users seem to need different reasons to adopt. Farmers and land managers tend to give more weight to financial incentives and economic realism. Other actors give stronger emphasis to field demonstrations, advisory training, and confidence building. And there are also some country-level nuances, especially around public funding, which suggests that adoption conditions depend on local support systems and advisory structures. So the implications for E-SPFdigits is that the same technology may need different adoption arguments. So economic value for farmers, practical interpretation for advisors, and credible field evidence for broader stakeholders. Moving to Survey 2, the perspective becomes broader. This survey looked at farm-to-fork stakeholders and explored how they perceive the soil contamination, soil management practices, and reduction strategies. The main message is that soil contamination is not seen only as a technical farm-level issue. Stakeholders connect it with food safety and food quality, but also with insufficient monitoring, knowledge gaps, and the need for a coordinated action. There is some variability between countries and stakeholder groups, but the overall signal is very clear. Soil contaminations requires a systemic response across the chain. And so for E-SPFdigit, this supports the soil, plant, food approach that we are taking. Monitoring tools are relevant not only for diagnostics, but also for prevention, governance, and food chain confidence. The next point is about how stakeholders perceive these different contaminants. Pesticide residues appears as the most visible concern participants had. They are easier for stakeholders to recognize and connect to agricultural production and food safety. Heavy metals are also seen as relevant, but perceptions vary more by country and by local context. PFAS and other emerging pollutants appear as more moderate concerns, but this should not be read simply as a lower risk. It probably reflects the lower awareness, the weaker monitoring experience, and the limited data availability, and kind of confirms what we saw in Survey 1, which is PFAS is not only a technical monitoring challenge, but also a knowledge and communication challenge. And for E-SPFdigit, this may mean that we can use familiar contaminants such as pesticides to help open the conversation, while the less visible contaminants require that we have a stronger work for literacy and monitoring support. Survey 2 also asked stakeholders to rate actions for reducing soil contamination and enhancing soil sustainability at different levels. The key message is that responsibility is not concentrated at farm level. At farm level, the highest rated action was sustainable practices, followed closely by nutrient management and on-site monitoring. But the strongest signal overall came from the industry level, the better control of industrial emissions and waste into soils. And this shows that stakeholders see prevention at the source as essential. So at policy level, the highest rated action was clear regulation of responsibility and liability. So stakeholders are not only asking for tools, they also need clearer rules and accountability. At consumer and public level, the strongest actions were support for sustainable farming and campaigns linking this soil health to food safety. So the synthesis is that different level points to different priorities: good practices at farm level, prevention at industry level, accountability at policy level, and awareness and support for consumers. One last point from Survey 2 is that digital tools are generally perceived positively. Stakeholders recognize their potential to support soil contamination monitoring and soil health monitoring. And this is encouraging, of course, for our projects, for E-SPFdigit, because it shows that there is openness to on-site and digital monitoring solutions. But the previous slides also show that positive perception is not enough. Stakeholders do not see digital tools as a standalone answer. They place them within a broader concept or context of sustainable practices, industrial prevention, policy clarity. So the message is that digital tools, they can play an important role, but they need to become trusted, understandable, and integrated into decision making. And this leads to the final question we try to address in the work package 1. What needs to be in place so that these promising tools can move from technical development to practical use? To close the stakeholder evidence section, I want to bring you one final layer that we had on work package 1, which were the inputs collected from the industry advisory board through semi-structured interviews and written replies. The main added value was to understand what these different actors need for digital tools to become usable in real contexts. So tech developers, distributors, and researchers focused mainly on validation, interoperability, standards, and data quality. And for them, tools need to work reliably beyond control settings and connect to other systems. NGOs, retailers, industry, and food safety actors highlight traceability, accountability, communication, and consumer trusts. For them, soil monitoring is also linked to transparency and food chain confidence, so that the message does not stress or worries the consumers, creating unnecessary public alarms. Authorities and policymakers pointed out to regulatory clarity, liability rules, recognition of methods, and policy support, although this group was less represented. And overall, the message is that practical uptake depends on more than the technical performance. Digital monitoring must become usable, trusted, and actionable from different actors in the soil, plant, food system. And to conclude, I would like to highlight 5 messages from the stakeholder evidence collected in E-SPFdigit Work Package 1. First, the problem is not the lack of relevance. Stakeholders recognize the importance of soil health, but on-site digital monitoring is still not widely embedded in the practice in our fields. Second, the strongest knowledge gaps appear where innovation is more needed: PFAS, emerging contaminants, and on-site digital tools. Third, that the digital tools are welcomed, but positive perception is not adoption readiness. We need to work on this adoption readiness. Users need reliable, understandable, and actionable outputs. Fourth, the soil contamination is a farm-to-fork responsibility. The response cannot be placed only at farm level. It also involves industry, policy, and consumers. And finally, uptake is socio-technical. So affordability, validation, interoperability, traceability, and regulatory clarity are as important as technical performance. And so the main message from Work Package 1 is that E-SPFdigit is not only bridging or bringing monitoring tools closer to the field, it is also helping to understand what is needed for digital monitoring to become trusted and useful for real decisions. And this is it from my side. Thank you so much for your attention and again for being with us today.
Thank you very much, Rita, for demonstrating how stakeholder perspectives can help shape successful soil health innovations and ensure that their uptake in practice. We now move to our final project presentation. Our final speaker is Dr. Mohammad Gwasvar from Ghent University. Mohammad is a postdoctoral researcher in the Precision Soil and Crop Engineering Group and is the scientific manager of NitroScope. His research focuses on precision nutrient management, digital agriculture, multi-sensor systems, and machine learning approaches designed to improve soil health and agricultural sustainability. He holds a PhD in soil science and leads NitroScope work on data collection and nitrogen management across different pedoclimatic zones. Today he will present a NitroScope UGent multi-sensor platform for high-resolution soil sensing 2026 field campaign insights. Mohammad, it's your turn.
Thank you, Zafiro. Thanks so much. I will share the screen.
Great.
Can you see my screen?
Yes.
Yeah.
Perfect.
Thank you so much for introducing. I will and providing this opportunity. I will not introduce again myself. Just my name is Mohammad Kaswar, and I'm postdoc in Precision Soil and Crop Engineering Group at Ghent University and responsible as a scientific project manager for the NitroScope. So, as you have seen the first presentation with my colleague Antonius, he talked about technology we are using. So basically technology is shared with both projects as we are coordinating both projects. So I will not go into details for the technologies, but I will show some results. First of all, I will introduce the NitroScope. NitroScope is the title is Scoping European Nitrogen Fluxes for Sustainable Nitrogen Management and Conservation Practices. So basically, this is a Horizon Europe Research and Innovation Actions started from October 2025. And this is a 4-year project. It will end in September 2029. And the main aim of NitroScope is to improve monitoring, understanding, and management of nitrogen fluxes across the Europe by developing advanced sensing technologies for continuous nitrogen monitoring and quantifying nitrogen losses and nitrogen use efficiency across the diverse European pedoclimatic regions, and providing region-specific emission factors, models-based decisions, support tools, and supporting farmer and land managers in adopting sustainable nitrogen management practices and contributing to more accurate European nitrogen budgets at country level and also European level, and also the future scenario analysis. So basically in NitroScope, we have 24 partners across the Europe, and also we have 9 intensive sites for continuous nitrogen flux monitoring 24/7 for 2 years, for 2 cropping season, and we have 5 pilot sites across the Europe. As you can see on the map, there are different countries, different pilot sites. There are 5 pilot sites for the different mitigation measures for the nitrogen contamination, for example, precision agriculture management and crop residue management. And so this is a combination of conservation practices and advanced precision management of the nitrogen. So I will not go into detail. We are using the same technology we developed at Ghent University. As you can see, we use this multi-sensor platform, and already explained well by my colleague Antonius. And this is also initial version or sketch of the multi-sensor portable system, but it is also explained well by my colleague. Basically, here I will add a little more. With this, we measure this include the different sensor, including the penetrometer for soil for the penetration resistance measurement, and load cell to measure the force used to penetrate into the soil. And it also consists of vision IR sensor, which measure the moisture. So basically, using these 3 important factors like the soil depth, force, and also the penetration resistance and moisture content, we predict the soil bulk density, which is important for the measurement of compaction. This was the initial version I just want to show, but it's more robust version. My colleague has already showed online ISC nitrate measurement system, so I will not go into details. So I will just today show the results of some field, because this project, this is the first year of the project. So we have scanned the field, and here I will show some results of high resolution maps using our online sensing platform. So this is results for field 1. We use partial least square regression models to calibrate the model from the vision IR spectra. And we predicted soil properties. As you can see, soil organic carbon, total organic carbon, phosphorus, potassium, pH, magnesium, calcium. And you can see these are all working good except the one, the lowest R scale you can see in the validation is for soil pH. But rest of the models are working very well. As you can see, the for validation, highest validation is 0.74. But although the soil pH is showing the lowest validation with R square 0.51. So basically, this is an independent validation. And RPD is 1.46. This is the least, but you will see in the maps, it still can capture the high resolutions in the field, spatial variability in the field very well. So basically, we use 190 to 100 soil samples. Basically, we collected, this was a 5 hectare field, I would say, and we collected around 20 samples. Then we have developed spectral library from the past soil scannings, and we spiked some samples to make the 100 to 120 or 90 to 100 set of samples to calibrate the model and then predict the soil properties. So these are scattered plot. For basically, these are the same results, but with the scatter plot, as you can see, we collected around 20 samples, and then we spiked the rest of the samples to make complete set of samples for the models to work. And these are for magnesium, calcium, and pH. The right side is, left side is basically calibration, and right side is validation. As you can see, for the soil pH, R square is 0.1 and RPD is 1.46. But when you see the maps, these are the results of those models. As we can see, it is well captured. For example, as you can see, this the upper end is more concentrated in mired soil properties. So basically, the above line, these are mired soil properties for this field, and you can see the spatial resolution is well captured in the predicted. So it means models are working well, and so that we can once we have these high resolution maps, we can identify the different fertility zone, different fertility levels to implement site specific or variable rate applications. For example, you can see in the soil pH, the upper end is relatively concentrated with the higher pH, and lower end here, as you can see, this is fully captured, but because there will be some differences, because these in the Meyer properties are only around 20 samples, but in the predicted they are more than I would say like 3000. So definitely there will be some differences, but most of the spatial resolution is fully captured. So this is a beauty of technology for online sensing to develop high resolution maps. As you can also see, for magnesium, the lower end is basically the low concentration, and the higher end, as you can see this corner where I have pointers. So basically this is a different concentrations of magnesiums are captured. And same for potassium. As you can see, there is some trends in the different soil properties. For example, for the calcium, if you see lower end, and for the potassium, if you see lower side is relatively more concentrated. So here we have to consider to apply less fertilizers. Same for predicted, the spatial variability is fully captured, and same for the organic carbon. You can see that basically also for the phosphorus, as you see, upper end is relatively more concentrated, and the lower, and this lower part is basically fully captured in the models. So by making these models and predicting maps, this is highly valuable to manage the field according to the different fertility level. So these are results for we use the same model but different calibration modes according to the soil properties. So these are the results from the different for the different field, and this was around 14 hectares field, and we collected 40 samples, but we have online scan like 6,000 online scans to develop the high resolution maps, and 40 samples we used we sent for chemical analysis, we used for the calibrations and calibrated the models, and then we predicted the soil properties. As you can see, the models are similar, they are working well. Cross validation, for example, for phosphorus is 0.7, and for validation it's 0.67. So these are somehow similar. Here pH is better than the previous one. And again, if you see the potassium, this is working well. Our scale for the validation is 0.76, and magnesium is also working good. So here, if we see, all models are working well, and the best calibration, as you can see, is for the total organic carbon. And you will see this differences captured well in the maps. So basically, we divide the data into 70% calibration and 30% for the validations. And then we use for the full online new set of sample, which is a full online spectra, like in this case, in this field, 6,000 spectra. We have predicted and developed the high resolution maps. So these are the scattered plots of the same results, as you can see, for the phosphorus, and for the pH working well, and for the total organic carbon. But here is some cluster, and there is some gap. This is because sometimes in our spectral library we don't have a similar range, because of samples are collected from different field, mostly from the Belgium, but also in the different part of the Europe. So when we make the complete set of sample, about 100 or 120 or 30, depending on the models, to calibrate the best models for the best predictions. Some samples are is not in the similar range for the current field we use for the predictions. That's why we will have some gaps. For example, if you see here, for the calcium, you can see here is calcium. The range is of soil calcium is different, and that's why we have some. But it still capture the high, resolution, and model is still working. So basically, here you can see this some sample from the different field, but we combine with the in chemometrics, we combine with the current field sample that we collected 40 samples. The rest of the samples are from the library, spectral library built during last 8 years. We manage that and to predict the soil properties. So these are results of those models. As you can see, this is these are basically the best maps output of the high resolution soil sensing, which is visible and near infrared spectroscopy based results. Basically, here are 40 samples. We to compare the measured soil property maps with the predicted soil properties maps. You can see these are the maps with the 40 sample, and here are the maps in the maps for the 6,000 Vision IR spectra. So this is these are the best maps we produced. You can see this is the technology working very well to capture the even micro level high resolution. So basically, this the resolution is about 1 sample per meter. So you can imagine in each meter we can measure the different soil properties, and you can see for the soil pH, this is captured very well, and same for the potassium, and similarly for the phosphorus and for the potassium, and also for the magnesium. As you can see, there is a higher concentration in this top right corner, and also which is reflected fully in the predicted maps. And there is also high calcium, and there is a very clear trend in soil properties. If you see, for example, the higher calcium you can see in the top right corner, and same higher soil pH in top right corner, but it means high calcium is affected negatively for the phosphorus, as you can see. So there is a strong correlation between these prediction between the soil properties. This can help us to make decisions to divide field into different parts, into different management zones, to apply different rates according to the soil fertility level, so that we can avoid over and under applications of fertilizers. This is what we call precision agriculture or precision management. So the conclusions are basically based on these results. For example, PLSR model showed good predictive performance for the all key soil properties in the both field, and the best results were achieved for phosphorus and magnesium in the field 1, and potassium and total organic carbon in the field 2. But we have seen the special models were working for the all soil properties, and it captured well special variability within the field that can help to manage the field according to the special variability. And the prediction of soil pH and calcium remains relatively weaker, although the special variability patterns were still captured in the field. So overall results demonstrate strong potential for online soil nutrient mapping using Vision IR spectroscopy supporting site-specific precision nutrient management. Thank you so much.
Thank you very much, Mohammed. And thank you to all our speakers for sharing such interesting and complementary perspectives on soil health monitoring, stakeholder engagement, and sustainable agriculture. We will now move on to our discussion and Q&A session. I invite participants to submit their questions through the Q&A box. We already have a number of interesting questions coming in. I will address the first question to Adonis, our first speaker. Deepak is asking, is gamma ray sensor used for the soil strength measurement?
Okay, thank you for the question. Well, basically, no. Basically, the gamma ray sensor is like a passive sensor, and it uses a crystal which can absorb the gamma ray emittance, especially very sensitive to metals such as potassium, uranium, thorium. So with gamma ray, we normally estimate the soil texture with very high accuracy and potassium. This is our published work. Now we want to expand it also to other metals. And but no, normally, like if we soil strength, we define the bulk density. No, for that we have the load cell do the job.
Thank you very much, Adoni.
Thank you.
Now the following questions are for Christina and STELLA project. Christina, Deepak is asking, is STELLA PSS available for public use? And what are the indices have been used to create a heat map for early pest detection?
Yes, so, some questions, yes, wait, I need to see it. So if I'm not mistaken, the first question was that the platform is public. Right now, through the domain it is, but it's mostly empty. The user can only see the location of our use case pilots and hasn't got any access to the rest of the subsystems. The goal is that it will go public once the models are finalized with their training, they have completed training, and that we are certain that they give correct results. So up until the closure of the project, the idea is that the platform will only work with data only from the use case pilots and not from external ones. So probably it won't be available to the public.
I will ask you the other question because I have what are the indices have been used to create a heat map for early pest detection?
Yes, so this is basically a mathematical model which is taking into consideration epidemiological characteristics of each pathogen with regards to the weather station data that we get every day. So it is a combination of daily weather station data and epidemiological characteristics of the disease respective to which model. So if we have 8 diseases, we have 8 different models corresponding to the characteristics of each disease. So there are no indices per se in the early warning. In the pest detection system, however, we mainly use NDVI to calculate in the back end, not in the front end. So in the front end, the user will not see NDVI values of the heat maps. They will see the actual detection. So the NDVI layer is being run on the background.
Great. Next question for you again, Christina. Muhammad is asking, can PhD scholars and agricultural researchers have access to STELLA services and data? Does it work only in Europe or the whole world?
So I will answer this question in reverse. The STELLA PSS right now, as I previously said, is said to be working only with the use case pilots since the complexity of the models is quite high. And we are limited to its use in these specific cases, but the idea is that it will expand within Europe. And of course, PhD scholars and researchers will have access once we are confident that every model is at the higher level of precision.
Thank you
So
very
it's
much,
a work
Christina.
in progress.
Thank you, Christina.
Thank you.
Next questions go to Rita. Maja is asking, what strategy did you use to get such a great number?
Well, we tried hard and we mobilized all the consortium partners, and we tried to contact and reach out to multiplier agents because it's very important to mobilize operational technical groups in the countries, advisory systems, partnership, this type of horizontal partners that can help to disseminate and give credibility to the surveys. We asked our advisory board and of course the sister projects and the EU initiatives, and by keeping persistence we managed to get good statistical samples.
That was great. Well done. Professor Moisen is asking, is it possible to explain how PFAS is measured by proximal soil sensing tools?
Yes, so it is basically the miniaturization of the procedure of the lab scale procedure. Okay. So, or this one is easier. So it's a small device that can be connected to a laptop, or so this is the molecular imprinted, it's an electrochemical sensor. And there is a miniaturization of the typical preparation of the sample. So to have it being done manually but quickly, or through the robotized platform, this has been then adapted. But I'm not sure if I was completely thorough on my explanation on how do we measure PFAS or PFOs.
Thank you very much, Rita. We don't have any more questions. Anyone else from the speakers wants to add something? If not, as we come to the end of today's webinar, I would like to sincerely thank all our speakers for their valuable contributions and all participants for joining us. Today's presentations clearly demonstrated how digital technologies, innovative sensing systems, stakeholder engagement, and sustainable nutrient management can contribute to healthier soils and more resilient farming across Europe. These efforts reflect the objectives of EU Green Week and the broader ambition of investing in nature through research, innovation, and collaboration. The webinar's recording and related materials will be shared through the participating projects' communication channels. On behalf of WHEATWATCHER, STELLA, E-SPFdigit, and NitroScope, thank you very much for being with us today. We wish you an excellent rest of the day and hope to see you again in our future events. Goodbye, everyone.
Thank you. Goodbye.
Thank you very much for this opportunity. Bye-bye.